or so, it seems. Okay? They're scaled down because it makes the picture a lot nicer. If you made them all the right length, the picture wouldn't be nearly so nice. They're all pointing in the right directions, and they're all, hopefully at least, relatively speaking, the right length compared to each other. And you can see the longer ones correspond again to the case where the level curves are closer together. And the shorter ones, which you can barely see, are when the level curves are further apart for that same contour interval of, what was it, 4.6 in this example. I don't know how Mathematica picks the contour interval. You can force Mathematica to pick a certain contour interval, but I don't want to show you that at the moment. Okay, so that's the idea of a gradient vector field, and we're going to especially work with vector fields a lot in chapter 16 and 17. We're going to be integrating them, find work done by a force. We'll be thinking about finding what's called the flow of the vector field, which essentially imagines that these are velocity vectors for water molecules in some thin layer of fluid. Okay? So that's the idea of a vector field. For the remaining time in class today, however, I want to do something different. I want to do a simpler example. So here's a simpler function here, x squared minus 1 squared, y squared, of how to think of a function whose domain is the two-dimensional plane and whose codomain is the real number line in terms of polar coordinates instead of rectangular coordinates, and something called the generalized chain rule. What I'm about to say is pretty tricky. You're going to really want to focus on my exact words. I'll try to say them as precisely as I can. We've got a function here, z equals f of x, y equals x squared minus y squared. You can pretend it's the temperature. It will have negative outputs so that your temperature scale could have negative outputs. So don't use Kelvins here. This function can be thought of in two ways here initially. You could think of this as just an operation, if you like. In other words, take an ordered pair of numbers and do this operation. Square the first coordinate, square the second coordinate, and subtract. So you can think of it purely operationally if you wanted to. For example, well, okay, this is a simple example. F of 1, 1 is 1 squared minus 1 squared is 0. All right? You also could think of it as a function on the plane. Pretend the board is the plane, where you have imposed a coordinate system, say a rectangular coordinate system, in the usual kind of way, and you think of this function here as telling you, say, the temperature of the plane at that point, because of the fact that the rectangular coordinates at that point are 1, 1. So here, with the formula, I'm thinking of it operationally. Do some algebra, in effect. Do some calculations, some arithmetic. When I drew this picture, I was thinking of it more in terms of the application. Imagine a plane, we're trying to describe the temperature, and we've got a point, we'd like to know the temperature of the point. This formula is giving us the temperature based on this thing being the rectangular coordinates of the point. But what if we wanted to use the polar coordinates of the point instead of the rectangular coordinates? This formula wouldn't work to give you the same answer. The polar coordinates, this is the rectangular coordinates at this point, the polar coordinates at this point are theta can be taken to be square root of 2 pi over 4. If we plug those numbers into this formula, pretending that's an r and that's a theta, it wouldn't give you the same answer. What formula would give you the same answer? I'm going to create a new function that's, well, it's going to be a function that's both new and the same somehow. In a way I'll explain it in a second. I'm going to call it f polar, and the reason I'm writing it like that is because that's the way I'll type it in Mathematica. F polar of r and theta. What I'd like this to be is I'd like this to be a function that gives me the same temperature for every point in the plane, however, using the polar coordinates of the points instead of the rectangular coordinates. How can I do that? Any guesses? It's actually not too hard. use that formula along with something else. Yes? Well, I did an r and theta in there. Don't replace x and y with r and theta directly. Instead, no guesses? Yeah, okay, we got some good guesses. Yeah, use x equals r sine cos theta and y equals r sine theta. Make those replacements. That'll give you the x and y coordinates of the point, and then that can be plugged into this formula to get the right temperature. As far as the formula for f polar, it's going to look different. X squared is going to be r squared cos squared theta. Y squared is going to be r squared sine squared theta. You could leave it like that. You could also factor the r squared out. And if you do, you also could use a double angle formula to write this as r squared times cos of 2 theta. That's not necessary to do, but it is something that does work in this case. Cos squared theta minus sine squared theta is equal to cosine of 2 theta. That's a double angle formula. All right, so again, it's a different operation. This says take a point, take an ordered pair of numbers, an r and a theta. You're doing something different to it. You're taking the first coordinate, squaring it, multiplying it times the cosine, 2 times the second coordinate. Those are different operations than what I did up here. But as far as the geometric interpretation in terms of coordinate systems, that gives you the same temperature at every point in the plane. Okay, so that's why this is pretty subtle. Okay, why would you want to do this? Well, sometimes this formula might be easier to analyze than this one. Now, in this case, it's probably this one that's simpler. But there could be other cases where this function is easier to think about. That's one reason why you might want to do it. But for the remaining 4 minutes for today, what we want to do is we want to try to differentiate z, not with respect to x and y, but instead with respect to r and theta. Let's just focus on with respect to r. That's all we'll have time for here today. And to do that, it's helpful to draw the following diagram. What is this diagram supposed to represent? It's labeled, first of all, with all the variables that you see. Z, x, y, r, and theta. Z depends on both x and y, so I put x and y below the z and put lines between z and x and z and y. X and y, by the conversion equations for polar coordinates, depend on both r and theta. So x depends on r and theta, and y depends on r and theta. Why am I doing this? Why am I drawing the diagram? It's going to be helpful in helping me figure out how to differentiate z with respect to r, for example. I'll find the rate of change of the temperature with respect to small changes in the radial coordinate. What you want to do is you want to look at the diagram and identify all the different paths through the diagram to get from that variable to that variable. In this case, there's two. This path here, or this path here. Along the line segments for each path, you want to label those line segments with the appropriate derivative rate of change of the top variable with respect to the bottom variable. So along this line, I'm going to label that line dz dx, or partial z, partial x if you prefer. Along this line, x is the top, r is the bottom. I'm going to label that dx dr. Along this line, I'll label this dz dy. And along this line, I'll label it dy dr. Two lines have gone unlabeled because that doesn't lead down to r. I could certainly label those appropriately to help me find derivatives with respect to theta. But I won't need those here with this example. What do? The chain rule here in this situation says multiply the derivatives along each path, dz dx times dx dr, and dz dy times dy dr, and then add the results. dz dx times dx dr, and dz dy times dy dr, those get multiplied, and then you add the results. This is what the generalized chain rule looks like in this situation, and again, the diagram helps you get it right. Give me a minute here. What does this equal in this situation? I'm not going to completely simplify it. What I'd like to do in the minute we have remaining is I'd like to replace dx dr and dy dr with what they equal based on the fact that that's x and that's y. Differentiate both of those with respect to r, and you get cosine theta for the first one, sine theta for the second one. This reduces to cos theta dz dx plus sine theta dz dy. And the final comment I'll make about that for today is that this can be thought of as a dot product. The vector cos theta sine theta dotted with the gradient of f with respect to the variables x and y at least. Gradient of f is a dot product, and we'll see next Monday that this dot product is helpful for understanding how to estimate this, for example, if you didn't have a formula based on looking at the pictures. Okay? So we'll see you next Monday.